So our first speaker for the evening session of the workshop is Maren Bennewitz. Maren Bennewitz is a professor of computer science at the University of Bonn. She's famous for her contributions to many areas of robotics, such as human-robot interaction, human-robot collaboration, humanoid robots, perception, SLAM, and many others. And of particular interest to this workshop is her contributions to the motion trajectory prediction and predictive navigation of mobile robots. In her talk today, she will present a recent approach for predictive navigation, which takes into account the goals of observed people. So without further ado, I would like to welcome Maren Bennewitz to our stage.
Thanks a lot, Andre. I will try to share my presentation.
Great.
Okay, can you see it?
Yes.
Okay, perfect. So thanks for your nice introduction and of course also for the invitation to this workshop. So service robots acting in human environments should of course avoid interferences with the users and act foresightedly so that they adapt their behavior to the users and not vice versa. And in this images here are 3 examples for actually undesired behavior. In the first situation on the left, the robot and the user are somehow stuck, so the robot is blocking the way of the user. In the second situation in the center, you see a robot closely following the user, which might be annoying and not desired. And on the situation in the left, actually the robot is too far away to help the user immediately when he calls for help. So our goal is to generate foresighted robot behavior so that the robot is close to the human if help is needed, but also at the same time avoids interferences with human motions. Existing approaches to foresighted and user-aware navigation typically apply extensive training for the trajectory prediction and are often also map specific. And often they do not consider where a user actually may need assistance. And that's what we are tackling. So we try to predict where the user needs the help of the robot and then generate foresighted robot behavior. So we use human motion prediction to anticipate where the robot service may be needed, as well as to avoid interferences. And yeah, we rely on the observation that humans typically move between objects and interact with them. And our goal is then to utilize this knowledge about the object interactions, about subsequent object interactions, to generate foresighted behavior of a service robot. And in this example, you see a user interacting with a cup, so carrying a cup. So the most likely next navigation goal of the user could be the table. So the robot would position itself close to the table in case help is needed, but also at the same time avoid interferences with the possible other paths of the user. So our approach learns transition probabilities for object interaction. So basically, we learn if a human interacts with an object A, how likely it is that the user will next interact with object B. And we use a map of the environment with locations of the relevant objects that we use then for the prediction of the navigation goal. So we integrate observation about the user and the detected object interactions to predict the navigation goal of the user. And this knowledge can then be used to generate foresighted robot navigation behavior by choosing poses that are close to the user, but at the same time avoiding interferences. So the robot is able to react quickly in case service is needed, but at the same time is not in the way of the user. To learn transitions of object interactions, we developed an approach to extract general object interactions from RGBD video streams. So we use an RCNN, which is trained on the Open Images dataset for object detection, and use the Open Pose system for the detection of the user and the estimation of the body skeleton. And we then detect object interactions based on objects the user is oriented to and that are touched by the user with its hand. So we estimate the orientation of the user and the hand positions from the body pose. And we then check whether there is an overlap between the bounding box of the object and the hand position, and whether they are close in the depth data as well. So here you see the tracked user pose, the estimated orientation. So the user is oriented towards the coffee machine, and also the bounding box of the hand and the coffee machine overlap. They are close, close in depth. So our system detects then an interaction with the coffee machine. Here's also a video demonstrating how our object interaction detection system works. On the left, there will be highlighted the detected object interactions, and on the right, you see the detected user, the objects, and also the body pose of the user. So I start the video now. So initially, the user interacts with a laptop, which is correctly reported by our system, then with a cup, and later on with a coffee machine. So using the system, we are able to infer or to detect object interactions, so to detect which objects the user interacts with. And from the extracted human object interactions, we then derive transition probabilities between subsequent object interactions. So these probabilities tell us then if a user interacted with an object A, the probability distribution of the next object the user will interact with. And we then use knowledge about the locations of irrelevant objects in the environment to infer likely navigation goals of the moving user and predict also the trajectory of the user. So in this case here, our system detects again an interaction with a cup. And based on that, we compute the possible next objects the user will interact with. These are most likely a coffee machine, as highlighted here by a dark green color, but it could also be like a table here, or the refrigerator, or some chairs here around this area. So based on the learned object interaction model and current observation, we can, and the location of the objects in the map, we can predict the navigation goal of the user. But of course, we additionally integrate observations about the user's actual movements and their body pose, and update then the probabilities of possible navigation goals using Bayesian inference as described in the following. So we want to calculate a probability distribution over the user's next navigation goal, the next object the user will interact with. So we calculate the distribution over the next object class given the user's observed position and pose. So for each known object in the environment, we calculate this probability here. And this can be done using Bayes' rule. So here we have the likelihood of the observed user position and pose, given that OI is a navigation goal times the prior probability. And the prior probability here corresponds to the interaction model. So given we know the last object the user interacted with, we can infer the probability distribution of the next object class the user will interact with using the interaction model. So we can just insert this here. For this prior probability, we insert the interaction model. So tau here is the last observed object the user interacted with. And using our learned interaction model, we can calculate the probability of OI being the next object the user will interact with. And what remains then is here to calculate this observation likelihood here. So basically here we calculate the probability that of the currently observed user position and pose, given that IO was the navigation goal. And this is easily done using the inverse distance of the user to the object position and the orientation difference of the user to the object. So basically here we calculate the shortest path on a grid map from the user position to the object location, and then calculate these inverse distances here. And with that, we have all terms that we need to calculate the belief about the user's navigation goal. So again, it's based on the interaction model, on the learned interaction model, given that tau was the last object the user interacted with. And here we have the observation model, which is based on the inverse distance to the object pose and the orientation difference. So using this, we can calculate the next navigation goal of an observed user. And this is our prediction that we evaluated first. So to test our prediction framework, we used 25 simulated office home-like environments, sizes between 100 and 150 square meters. And yeah, these environments contained on average like 25 objects from 15 object classes. And we recorded trajectories of users in these simulated environments. And for training the interaction model, we used a data set of 161 sequences containing several subsequent object transitions. And then we evaluated the prediction. So for the quantitative evaluation of the navigation goal prediction, we use a separate data set of 64 trajectories between two objects. And then we generate an observation every second as long as the human is moving. As I said, these experiments were carried out in simulation. And we evaluated the prediction with and without knowledge about the last object interaction, because it can also be, of course, that the robot does not always observe the human. So we have to marginalize about the last object the robot interacted, the human interacted with. And in this case, the robot only observed the user during the movement, but not the initial object interaction before the user started to move. So after each update step, we check whether the predicted most likely navigation goal corresponds to the true navigation goal. And if so, we count the prediction as correct. So we then evaluate two metrics. One is the prediction accuracy, which is the number of correct predictions divided by the total number of observations. And then the average position on the user's trajectory from which on our system continuously returns the correct navigation goal. So these are the two metrics we used to evaluate our approach with and without last object interaction observed. And the results are here on this slide. So as can be seen, we achieve an average prediction accuracy of 0.67 when the robot observes the last interaction, the last object interaction, and without the last object interaction, we achieve a prediction accuracy of 0.48. And the system is able to continuously infer the true navigation goal after 28% of the trajectory of the user are observed. And if we don't use the last object interaction, then after 52% of the trajectory. So yeah, this evaluated our prediction framework. And now, of course, we want to use this prediction to generate foresighted robot navigation. So first, we use the belief about the user's navigation goal to determine the best robot position where it should move. So and the service robot needs to place itself so as to be close to the user in case service is needed, as explained in the beginning, but at the same time, of course, it shouldn't interfere with the user. So we evaluate the grid cells using a cost function, and here we take into account the distance to the user's possible navigation goals weighted by their probabilities. So basically, the lower cells get a lower cost if they are close to likely navigation goals. So we sum up over all possible navigation goals, calculate the length of the cells to the navigation goal, and multiply this with the likelihood of this object being the navigation goal of the user given the current pose. So this is basically our prediction we calculated before, and now we use this to evaluate the grid cells, taking also into account the length of the grid cells towards the navigation goal. And here's an example. You see again, here are objects in the environment which are dark green. These are more likely navigation goals. And here the darker blue color corresponds to lower cost. So in this example, this position here would be the best robot location because it's close to possible likely navigation goals. Yeah, it has a low average distance to those goals. Yeah, for path planning, we then consider constraints derived from studies about human comfort and predict the user's path, given the belief about their navigation goals, which is shown here. These are the possible navigation goals. So we predict the user's path towards these navigation goals and perform then time-dependent path planning for the robot, taking into account constraints like social constraints of humans. So from proxemic theory, we know that humans have personal space regions around them that the robot should not enter. These are, for example, the social zone, which is a circle with a radius of 1.2 meters around the human, and the interpersonal space region in front of the human. So these regions the robot should not enter if there are other positions possible. And also here the area in the back, so positions up to 5 meters behind the human, the robot should not enter because humans do not want the robot to directly follow them. So these cells here have increased costs, and these cells here should be avoided by the robot if possible. So we predict the user's most likely navigation goal and also the path towards the goal, which is just the A star path on the map, and determine first the best robot position. And then we apply time-dependent path planning to consider those human comfort constraints I just introduced. So basically we plan then on a 2D grid map of the environment with an additional time dimension and consider the predicted human motions. And in this way we can calculate the best robot or the most cost efficient robot path towards the best robot position, calculated here in the first step. And this path then considers all the human comfort constraints. I have here a video showing our approach. So on the left here, you will see the camera image of the robot and the detected user and also objects. And on the right, you see a map of the environment. And again, here, the objects which have a high likelihood of being the navigation goal of the user will be in dark green. You see here in this light violet, basically social space around the human, the robot should not enter. I start the video now. So first, the robot predicts the user to move to a location somewhere here. So this would be the best robot position, since it is close to those likely navigation goals. But as the robot moves into this direction, it notices that the user is actually going in this direction. So it updates its belief, recalculates the most likely navigation goals, which are now more in this area here, calculates its best robot position. Now the user entered this room here, so the robot would also enter here. But as the robot approaches this room, it observes the user again exiting from this room, recalculates the most likely navigation goals of the user, calculates the best position for itself, and then takes the opportunity to actually move fast with a faster velocity to overtake the user and arrive at the predicted goal location even earlier than the user itself. So as you see, yeah, the robot avoided just following the user, which is not desired, but predicted its navigation goal constantly if, as more observations were obtained, and corrected and updated its belief and its best position. Yeah, and that's it actually. So I presented an approach for foresighted robot navigation by anticipating where service is needed. So we avoid just following the user, which the users normally don't like. And to realize this, we exploit knowledge about object interaction transitions. So we learn interaction models, so subsequent objects the user interacts with, and use this to infer navigation goals, give them a map of the environment with the locations of the relevant objects. And yeah, we learn this interaction model first from RGBD data and use it then to infer the user's navigation goals and predict the corresponding path. And then we applied time-dependent path planning, considering constraints corresponding to human comfort to generate then foresighted and user-friendly robot navigation behavior. So the robot is able to position itself close to the user to provide service quickly if needed, but at the same time avoids interferences with their predicted path. And obviously, our approach heavily relies on the detected object interaction. So far, we assume that the user is more or less always in the field of view of the robot, which might not be the case. So in the future, we are also planning to use like an let's say tech-based system, so an ultra-wideband real-time locating system for the user and the objects in order being able to detect the object interactions also when the user is not in the field of view of the robot. Yeah, that's it for the moment. And if you have questions, please ask them now. Thank you.
Thanks for the very interesting talk. Do we have questions in the audience, maybe?
So Andrea, I have a question.
Okay, yeah, thanks.
Yeah. So thanks, Maren, very interesting work. So the question is mainly now, what happens if you have multiple humans in the scene? Does this model still work if you have a lot of occlusions, right? And also, does it consider any human-human interactions?
Mm-hmm. So I must say that the approach was basically developed for a service robot acting in the home of a single person. But of course, if there are multiple persons and the robot can distinguish them, assumed they have all individual object interaction model, then the robot would still be able to provide service to the individual persons, but it must somehow be specified which is the main person, I would say. So I guess it would be difficult for the robot to keep track of all the people and be at their navigation goals. So yeah, as I said, the approach was developed for basically one person and the robot. And when there are several persons, we would need some kind of a priority scheme. Does this answer your question?
I meant also if other persons are, let's say, interacting with the person that we want to follow, right? Mm-hmm. Of course, these interactions will change the way this person is behaving. Yeah. Do you also consider these interactions? So...
Okay, no, currently we don't consider this because we did the experiment, or the approach was designed for one single person. That's it. Yeah.
Yeah, clear.
Thank you.
Thanks.
Okay, there is a question in the chat. Actually, one question: how does using an RGBD camera help over just using a single RGB camera?
Mm-hmm. Yeah, very good question. I mean, we use the depth information to infer whether the hand and the object are actually close to each other. If you just use an RGB camera, it can be that there are objects in the background close to the hand, so it's difficult to distinguish this. Actually, we did it first with only RGBD data, but then we noticed that we need the depth data to really see whether the hand and the object are close.
Thanks, says the person in the chat.
Thank you.
Do we have more questions? Maybe I have a couple of questions to the detection of interesting objects. I think it's a really cool idea to understand what in the environment could be the goal of the person, but I wonder, how does your method handle the cold start? Namely, do you have a predefined set of interesting classes of objects, or the robot in an unfamiliar environment will be able to somehow understand over time or automatically detect where is the coffee machine, where are the chairs, where are the sofas, and so on?
Yeah. So our idea is actually that subsequent objects interactions are general. So like for office environments or for home environments, people have similar patterns to move between these objects. And of course, we need somehow to define what relevant objects are, but then we can learn these interaction models, the transitions between the objects. And the idea is then to transfer this knowledge to known maps. Of course, we rely on the positions of the objects and environment, but the idea is to have first trained a general interaction model and then transfer this to specific environments without retraining. This is the idea. Of course, yeah, we need to somehow define what relevant objects are, or what we also could do is summarize objects to like activity regions, because typically in one activity regions, like my desk here or so, there appear the same objects and as on your desk maybe. And also in home environments, the same objects appear in the kitchen and on the dining table or on the office desk, whatever. And we could also do like a clustering of these objects and then predict the motions between typical activity regions to make it the approach more efficient, let's say.
Yeah, that's pretty interesting. Yeah, thanks for your reply. Do we have we have a raised hand, so could you please name your question then?
Yes, hi, thank you so much for the great talk. I'm really interested in this, the model that you've generated after this with the transition probabilities. So I'm wondering about, so for example, in computer vision, when there's generative models, GANs, for example, that generate some next possible action, people might subjectively evaluate them to say whether it looks real or not. So I'm wondering about these generated probability distributions. Do you, even maybe from a qualitative aspect, do they seem possible? For example, people are not going to go to the coffee machine before getting the cup, or could you give a little bit more insight about these models that are generated?
Okay, so basically we only calculate the next navigation goal, and you were talking about sequences of navigation goals, right? Or
that is true, yes.
Like dependencies. This is very interesting, and actually we are also planning to use something like that in the future, but currently we only predict the next navigation goal, let's say, but it would be interesting to apply like an LSTM or so to really have a sequence, a history of object interactions and use that knowledge. And exactly that what we were talking about could be integrated then, and maybe would even improve the prediction.
Thank you very much.
Thank you.
All right, I guess if we don't have any more questions from the audience, okay, then thanks again, Maren, for the excellent talk, and we will slowly transition for the next.